Thank you for your interest in new developments in strain hardening modulus for polyethylene pressure piping applications. Before we start, I'd like to say that Brian Hauger Consulting is a B2B plastics consulting business with a global reach. Check out our website at www.brianhaugerconsulting.com and see why our motto is, our only product is a satisfied client. This presentation was originally provided to the Polyolefins Conference in February of 2017. As an overview, this presentation will be organized in several parts. I will quickly establish the objectives for this presentation. In the introduction, I will familiarize the audience with two terms that will be important for the presentation that relate to the tensile testing of polyethylene materials. Those terms are strain hardening modulus and natural draw ratio. I'd like to discuss several case studies, starting with a publication in 2005 that eventually led to the creation of the ISO 18488 test method, which is the focus of our discussion. I will then talk about three additional case studies. One from 2012, which looked at the statistics of strain hardening modulus testing, one in 2015 that correlated log of PENT to strain hardening modulus, and finally, a second and more detailed correlation study of log PENT with strain hardening modulus, which explicitly used the ISO 18488 test method. I'd like to present my own work combining the statistical analysis from 2012 with the 2015 case study, as well as to bring you up to date on my own efforts to offer a test method for strain hardening modulus developed in the consensus environment of ASTM. And finally, I will draw a few conclusions. As objectives, in this presentation, I would like to introduce you to the ISO 18488 for the measurement of strain hardening modulus, to illustrate the promise of strain hardening modulus to reduce costs and time requirements to obtain useful information on slow crack growth and potentially to replace the PENT test, to consider the statistical relevance of ISO 18488, and to update you on ongoing efforts to realize the full promise of strain hardening modulus in the plastic pipe industry in North America. But before we take a deeper dive into these plastic piping topics, let's first take a couple of minutes to understand the natural draw ratio and strain hardening modulus. Here, I'm showing my favorite digital microscopic image of a craze zone in polyethylene. In this single image, you can see the crack opening nature of the failure, along with the bridging fibrils which cross the craze zone. These bridging fibrils oppose the opening of the crack through their resistance to continued elongation. The net effect is commonly referred to as crack tip blunting and can temporarily stop the progression of the crack through the material. Eventually, the fibrils thin and rupture, with the crack advancing further through the material. Since the mid-1990s, researchers have been examining the relationship between these bridging fibrils and the drawing portion of the stress-strain curve for polyethylene, amongst a number of other relationships. Eventually, this has all been formalized as ISO 18488. So at the first mention of the stress-strain curve for polyethylene, this is the image that jumps into the minds of many people. In this simulated or idealized stress-strain curve for polyethylene, you'll see several features that are familiar. At the start, we have a rapid increase of stress and strain that gives rise to the Young's modulus or elastic modulus. The load increases with increasing strain until we near the yield point of the material, where there is a plateau and we achieve yield. Then the load starts to decrease as the cross-section in the yielded region thins. If this is a high-density polyethylene, perhaps we'll see the yield stress somewhere between 3,000 psi and 4,000 psi, and a yield somewhere between 8% and 10% strain. Continuing to strain past yield, we obtain some type of an arch shape before reaching the bottom of the arch, and there is a flat or nearly flat region at the bottom illustrating the drawing of polyethylene. Many of us stop there, but some continue further. Here you see a full stress-strain curve to rupture for an actual higher performance pressure pipe grade of polyethylene. we see that following yield, the region of drawing is at first stable as the necked region of the gauge continues to elongate under load. Eventually, a long fiber-like section can extend over the majority of the gauge until a strain hardening limit is reached. At this point, load once again rises rapidly with displacement and eventually terminates in the test specimen breaking. In this example, the apparent stress at break is higher than the stress at yield. However, two features are of interest for our further discussions. One will be the natural draw ratio, and is the strain at which the load first increases following the region of fiber drawing. The second is termed the strain hardening modulus, and is the slope of the region with increasing load following the natural draw ratio. These are important concepts and will be referred to throughout the talk. Here you see the true stress strain curve to rupture, which may be unfamiliar to many of us. It requires a simple conversion from apparent to true stress by making the common assumption that there is a conservation of volume in the gauge region. In ISO 18488, we consider the strain hardening region to start at a true strain of 8 and extend to the point of maximum stress, but not above a true strain of 12. The linear fit of this region gives us our strain hardening modulus. The origin of the current test method, ISO 18488, comes from this 2005 publication by researchers from SABIC and DSM, who proposed the use of the slope of the stress strain curve above the natural draw ratio and termed it the strain hardening modulus. The paper showed that strain hardening modulus was useful as an index of the ESCR performance of polyethylene. It is worth noting that all tensile tests were conducted using an ISO 37 Type 3 tensile bar in an elevated temperature test frame at 10 millimeters per minute extension rate using an optical extensometer. Here I have republished the data from that 2005 paper by listing the data in order, starting with the smallest ESCR values and progressing to the largest. One can see a fairly clear trend with increasing ESCR values showing the largest strain hardening modulus. Here the data from that previous table is plotted, but I don't show the non-failure data point from the previous table. The exceptionally good quality of the correlation between the strain hardening modulus and the log of ESCR failure time in hours is reflected in the high value of goodness of fit. This implies that one can assess the likely failure time of blow molding and pipe resins in the ESCR test by conducting the quick and easy strain hardening modulus test. Perhaps the apparent generality of the principle of using tensile data as a metric for ESCR implies a potential relationship to all other slow crack growth tests. This slide shows the 2005 publication details. Many of those details are similar but not identical to the ISO 18488 test method. For example, in the 2005 study, they compression molded polyethylene pellets into a thin sheet at 160 Celsius, while in ISO 18488 they use 180 degrees Celsius. In the 2005 study, the thickness of that compression molded sheet was approximately 0.3 millimeters, and that is the referee thickness in the ISO 18488 test method. But the ISO test method also allows a thickness of 1 millimeter and provides tolerances for the thicknesses. Here, pellets are heated first for 5 minutes before compression, while in the ISO test method, the initial heating time is 5 to 15 minutes. In a 2005 study, they reported the use of kilonewton loads, while in the ISO test method, they specified the application of 5 megapascals of pressure. Here, the thin sheet is cooled to room temperature under load, but in the ISO test method, they allow you to remove the load at any temperature so long as it's below 40 degrees Celsius. But in both test specimens, you anneal the thin sheet by heating to 120 degrees Celsius for 1 hour and then slow cooling. In the 2005 case study, they just turned off the heat, but in the ISO test method, they require slow cooling at an average rate of less than 2 degrees C per minute. In 2005, they used ISO Type 3 tensile bars as the test specimens, but in the ISO test method, they have slightly modified the geometry of the ISO 37 Type 3 tensile bar. Most critically, both studies require the use of an elevated temperature test oven at 80 degrees C and the use of an optical extensometer to measure strain. But the strain rate is a little bit different. In this case, it was 10 millimeters per minute, but in the ISO test method, it's 20 millimeters per minute. To a very large degree, the ISO 18488 test method requires similar molding, annealing, a similar tensile bar, and similar measurement of strain using an optical extensometer. Here I'm providing those ISO 18488 conditions for you again, just for the sake of clarity. I think that you will agree that many details are similar between the 2005 case study and the ISO 18488 test method. Unfortunately, there is one other detail that the 2005 case study and the ISO test method have in common. No statistical analysis is provided in either study. Of course, one of the most important considerations for establishing a correlated relationship between strain hardening modulus and any other measure of slow crack growth resistance will be the statistical variation in the measurement of both values. In the next slide, we will take our first look at information on statistics of the ISO 18488 test method. For the statistics of strain hardening modulus, we look to a presentation from Plastic Pipes 16 in 2012 by authors from Kiwa Technology. The conditions used in this study were identical to the ISO 18488 test method and include a round-robin study conducted on PE80, PE100, and PE100RC, or a highly stress crack resistant material. In this study, 8 laboratories conducted testing on those 3 materials, with replicate measurements varying in number from 3 to 9, depending on test lab. The average value for strain hardening modulus is reported in megapascals, along with the composite standard deviation. In the final row, I have converted those standard deviation values into a percentage of the average strain hardening modulus. Looking at the first column for resin A, the paper also describes the exclusion of some non-compliant resin A data, which significantly reduces the standard deviation below the values shown here. If that data is excluded, then the standard deviation for resin A is reported to drop to just 4.4% of the average value. So for the sake of simplicity, let's just consider that the standard deviation for strain hardening modulus is approximately and uniformly 5% of the value of strain hardening modulus. Remember that value, as we will return to it soon. Another critically important paper was published by researchers from Rey Juan Carlos University in Spain, which correlated strain hardening modulus and log PENT for the first time. Unfortunately, this paper did not use the ISO 18488 conditions. However, the paper demonstrated that strain hardening modulus was useful as an index of the PENT performance for various polyethylene grades. Unfortunately, the actual data we need are not published in table format in the 2015 paper, so instead, the data shown in the table on this slide for both strain hardening modulus and PENT failure times were estimated based on a figure in the 2015 paper. Also, unfortunately, we note that the largest PENT value in this paper reaches a maximum at about 3,000 hours. Therefore, this paper does not address the full range of performance available in the current market, since some commercial materials now report PENT values in excess of 10,000 hours. However, one can see a trend that increasing PENT values show increasing values for strain hardening modulus. By taking the log of the estimated PENT value, I now can construct a familiar plot shown on the next slide. Once again, an exceptionally good correlation coefficient implies that one can assess the likely failure time of PE resins in the PENT test by conducting the strain hardening modulus test. But while the researchers mentions that they measured strain hardening modulus in triplicate, there are no error bars provided in the report. Now, please recall the previous result in which the standard deviation was approximately 5% of the value of the strain hardening modulus. What would happen if we applied that statistical result to this study? If we assume that statistical variation in strain hardening modulus is normally distributed about the mean, then 3 times the standard deviation should account for 99.7% of the population being studied. So I've added a 4th column to the previous table, which calculates 15%. That's 3 times the 5% value we've discussed previously. 15% of the previously estimated values of strain hardening modulus, and represents both the positive and negative variance in strain hardening modulus. We see that a strain hardening modulus value of 28 megapascal can be represented as 28.0 plus or minus 2.1 megapascal, and so on down the table. Now, this relationship is pure speculation, but let's take it one step farther and now replot the previous chart with this statistical model superimposed on it. Here, I've taken the previously presented chart and I have superimposed an oval over just 4 of the previous data points, with the x-axis range for the oval corresponding to the statistical variation column shown in the previous table. Purely for the sake of illustration, I have also added lines defining the negative and positive limits of the statistical variation. I believe this figure is illustrative since you can visualize that for a PENT value greater than 1,000 hours, so that's log 3, you need a minimum average value of 38.5 megapascal if you're going to fully account for the statistical variation. And let's be clear, in many scenarios, the direct measurement of PENT is the only result the industry is currently willing to accept. However, the opportunity to obtain a result in perhaps 72 hours rather than waiting 1,000 hours for the PENT result is probably attractive in some other scenarios. And the attractiveness of such an approach becomes more clear if the desired PENT value is 2,000 or 5,000 or 10,000 hours. As I mentioned previously, those types of very high PENT performance were not reported in the 2005 study, but such a study does exist and continues to show a linear relationship between log PENT and strain hardening modulus up to a limit. In 2016, authors from Rey Juan Carlos University again conducted a study to correlate strain hardening modulus with log PENT. Their figure is reproduced here with log of PENT hours at the left and strain hardening modulus at the bottom. You see that 3 data sets are actually presented, one for Ziegler-Natta, 1 butene copolymers, 1 for chromium 1-hexene copolymers, and 1 for a blended system from an iron-based catalyst and a metallocene catalyst. And while this plot may raise as many questions as it answers, it does show a true ISO 18488 result in the x-axis. And, as usual, it shows good linear correlation over several decades of PENT performance, spanning up to 10,000 hours of PENT and potentially beyond. And it does show that for the 2 most common commercial catalyst systems for pipe resin, the departure of the black and red lines is likely not statistically important until you obtain values well in excess of the 500-hour PENT value currently mandated for pressure pipe resins to qualify for PE 4710. Therefore, I have taken action and initiated a project to create an ASTM test method titled Measurement of Strain Hardening Modulus on Polyethylene Materials Used in the Manufacture of Stress-Rated Pipe. It is hoped that this effort will provide ASTM participants access to a test method which meets the needs of industry. At the point that the test method reaches finalization, it is anticipated that a round-robin study will again be conducted on the strict scope of the ASTM Strain Hardening Modulus test method. A particularly favorable outcome would be to obtain an ASTM test method that retains any critical aspects of the ISO test method. I believe it is also critical to understand if carbon black and pigments can be included in the resin studied, or if the test is only applicable to natural resins. I hope I have not only introduced you to the ISO 18488 test method, but that I have also convinced you of the potential viability of using this tensile test to replace PENT testing, at least in some scenarios and in a fraction of the time currently required to obtain those results. I hope I have also provided you with an appropriate consideration of the statistical possibilities of strain hardening modulus. Finally, I am glad to invite this audience to participate in the current industry efforts to create an ASTM test method with proper precision and bias testing that includes pigments and may be useful to the industry in the future in a variety of ways. Thank you for your time. I'll take any questions you may have. Feel free to contact us by phone at the number shown or visit the link provided in this post.